sure that you know who's speaking and who's putting this beautiful event on. All right, so welcome everybody to the first in a series of webinars on JP3's Verax technology and its applications in the hydrocarbon processing industry, and what if measuring hydrocarbons could be quick and easy for your business? And what if the same solution can be deployed in every basin for everybody? Now, just a few words on JP3. JP3 is a wholly owned subsidiary of Flowtech Industries, an NYSE listed company. JP3 is a leader in the oil and gas measurement and analyzer market, serving the upstream, midstream, and downstream segments for real-time process control, quality monitoring, and custody transfer. JP3's game-changing analyzers provide real-time information that enables customers to maximize the value of their hydrocarbons. This presentation has been put together by Making Measurements Matter. That would have been where you receive your emails from and stuff, guys. So if you have more questions for us on that, that's how we've been communicating with you. And it's dedicated to the education of measurement-related solutions globally. And your speaker today is Mr. Phil Harris. Phil is the president at Insight Analytical Solutions, which is a Calgary-based integrator, distributor, and developer of process analyzer and sampling technology. He has a Bachelor of Science in Physics, Masters of Science in Chemistry, and 35 years experience starting in the nuclear industry and coming to Alberta to develop process analyzer solutions for the oil and gas industry in '93 with Western Research. He's a fellow of the ISA, recipient of a Lifetime Achievement Award for Technical Innovation, the ISA Award for Excellence in Technical Presentation, and a 7-time recipient of the GTFK Award for the Best Technical Paper. He's also the author of over 30 technical and research papers, and he is a JP3 partner in Canada. So without further ado, I will just let you guys know that there will be a question and answer period at the end, which most of you have heard me talk about already. And Phil just wanted to do a really special shout out because there's a lot of colleagues at JP3 that would like to probably stay on, answer some questions, and just stick around if you guys want any more information on anything. I'm not sure what Phil's schedule is, but I'm sure he's happy to spend a whole bunch of extra time with everybody. And if he's in the house, Mr. Phil Harris, are you in the house?
Well, it sounds like I better be, eh? All right, thanks, Chelsea. Yeah, thanks everybody for coming. Big thanks to Chelsea and her team. Of course, they always help to set these things up and both entertain people, soften the crowd for me a bit. Dougie, just saw you showed up, man. How you doing, buddy? Greg, good to see you. And so it's great. I mean, as you probably noted, we kind of have this all organized in terms of how you're going to get information, how you're going to invites, how to get here, and hopefully all the information you're going to need by the time I'm done as well. So again, I guess I'm going to start also by thanking both JP3, they're kind of our host, and of course Flowtech, for having me help to put this on with them. I've been working with JP3 now for, it's got to be coming close to 7 years now. I started out doing some consulting work with them, and they're really the reason why Insight Analytical started as a company, because we said, this technology is great. I'm a spectroscopist by trade, was working with them on this technology and said, how are we going to bring this up to Canada? And so we've had the opportunity to work with them for a number of years now. And hopefully I'm going to get a chance to kind of give you some information. We're going to start out with this. We're going to probably do this as a webinar, or we're going to do this as a webinar series. And this first one's going to be a little bit more about the hardware, what's unique about the hardware that they use. And then the future ones, we're going to talk a little bit more about chemometrics and how we do some of the modeling. And then further on after that, a little bit about how we implement that into process control systems. But in each one of these, we're going to try to address some key applications along the way as well. So like today, we're going to talk primarily about near-infrared spectroscopy, how it works, what's unique about how JP3 does it, what we've tried to implement in the field so far, and what things we're working on. And I can start a little bit with a kind of an overview of what we're going to touch on today. So I'm going to start out with talking about, who are we, who are all the players involved. Chelsea's already given you some information on that. And oh God, I'm such an awful person. I keep on recognizing Chelsea, and we have Teresa here helping her as well. So hi, Teresa, thanks for your help. So we're going to talk about kind of JP3 insight, making measurements matter, how that all fits together. And then we're going to talk about kind of what's new. I mean, infrared spectroscopy has been around for a while. And so we want to talk about what's unique in what JP3 does and in how we've implemented it in some upstream, midstream oil and gas type applications. And we'll talk a little bit about what works. Specifically, we're going to kind of focus on condensate stabilization, crude oil stabilization, gas plants today, and then kind of where we're going with this next. So from that who are we side of things, JP3 is a company of Austin, Texas. They're an equipment and information company that develops and sells online analyzers and data analytics solutions. And JP3 has brought some unique measurement capabilities together that enables us to kind of implement things we've perhaps tried to do in the past in a way that's more or less maintenance intensive and easier to kind of implement in online type applications. As Chelsea mentioned, Inside Analytical is a systems integrator out of Calgary. We're a distributor and a technology development company as well. And we've had the privilege of being JP3's business partner and distributor in Canada since the launch of the technology in Canada. And Making Measurements Matter has been a vehicle, if you like, a website that we've been trying to put together, get more people involved in, to be able to give kind of educational and informative webinars, whether it's about a product, whether it's about an application, or whether it's about a measurement issue. And as Chelsea mentioned, you're going to probably see some emails come up. We're launching some new programs. We're going to try to get some end users coming in and talking about, hey, I have a measurement problem I don't have a way of solving right now. And then get people being able to say, well, we may be able to help you with finding a solution as well. So Making Measurements Matter is kind of dedicated to education, really related to the measurement industry and measurement solutions globally. So when we talk about kind of what's new and what we've changed or what has changed in these systems to make it more appropriate for certain applications, there's kind of three places where this has come together. One has been in what's changed on the spectroscopy side, how we've changed what type of spectrometers we're using, and that's allowed things like better calibration transfer, the ability to put these out in the fields in difficult environments. Talk about some changes that have gone on in the past decade over in chemometrics, and now we do better jobs at data analysis. And then also, and this is part of the big thing really, I mean, I just spent the morning teaching a course on how to design analyzer sample conditioning systems. And one of the common problems in most analyzer installations is related to sample conditioning. So if we can minimize those sort of issues, we can kind of maximize the utility of some of our measurements that we do. So since the type of technology we're using here is near infrared absorbance, I'd like to start off briefly by just doing a quick kind of introduction to the concept, if you like, of what we mean by absorbance spectroscopy. So when we're going to do absorbance spectroscopy, we shine a beam of light through a sample. And we look at what colors of light got taken away, more so than the light that gets transmitted, if you like. So if I wanted to determine how green something was, at first blush, you'd think, well, I'm going to look at how much green light goes through it. The problem with that is, if I shine green light through this glass of water, it'll go right through. The same way as if I put a green filter there. So I can't tell how green something is by how much green light it transmits, but I can tell how green it is if it takes red and blue away and still transmits the green light. So in absorbance spectroscopy, we're often looking for what colors get taken away, what wavelengths get taken away. And that gives us information about the fluid or the material that we're trying to measure. It's good thing I have this glass of water here. So we identify something as green because green gets transmitted, and this is the important part, that red and blue are absorbed. So in absorbance spectroscopy, we're looking for kind of how much light gets taken away. This is important to us because when we start to look at the spectrum of light, we typically think of this, red to blue spectrum, what we refer to as visible light, and what we can see and determine there. But there's a lot of other wavelengths that we can use that pass information off to us. And so if we put something like a crude oil sample in, it absorbs almost all of the visible light. This isn't actually a crude, but it's a condensate, a natural gas, heavy condensate. And you can see it's kind of pretty dark and it doesn't pass through much light at all. And so I can't get an awful lot of information about what's going on in this material if I look at the visible part of the spectrum. But as I go beyond the visible, when I go past the red, which is what we refer to as the infrared, and if I look just past the red, so close to where the red is, we call it the near infrared. And when we start to move our wavelengths out there and look out there, we start to see that all that background, how dark the stuff looks, starts to drop away. And as we move out in wavelengths, we get out to about 1,600 nanometers or so. And suddenly all the hydrocarbons start absorbing. And we get these absorbance bands, these shapes that we can look at. And those give us information. The shape of every hydrocarbon that absorbs is slightly different. And we can identify what hydrocarbons are there by the shape of the infrared absorption that we see out in this wavelength region. And we can identify how much of them is there by how strongly it absorbs the light. So by looking in the near infrared, we can get information about qualitatively about what's there and quantitatively about how much of it is there. Now, it's not like we just developed this idea or this concept or this capability. It's been around for over 100 years. Around 1900, Koblenz was one of the first chemists / physicists who started really looking at infrared spectra. His spectrometer was probably close to the size of the room I was in, and he starts looking at infrared spectra and comes to the conclusion that basically every hydrocarbon molecule has a slightly different infrared spectrum. So, we've known that we can use infrared spectra to identify hydrocarbons for a long time. We've started to see industrial applications of this in the 50s, especially to look at things like water. Water is a really strong absorber in the infrared, and it became a way that we could say, how much water is in my acetic acid? How much water is in my alcohol? How much water is in my gasoline? We used infrared spectroscopy to determine sort of water concentrations. As we move forward in time, getting closer to the 80s, another Canadian company, giving them a lot of respect and credit, Beaumont out of Quebec, developed near infrared infrared spectrometers, and specifically Fourier transform type infrared spectrometers. And these could get whole spectra, a lot of spectral information all at once. Do it fast, get high quality data, and that enabled them to start taking measurements out to process applications. But, and this worked great, works fantastic in refineries, petrochem plants, where there's lots of people around who can do maintenance. But the issues were, some of the things on the spectrometer, light sources, spectrometers themselves, moving parts, part failures, maintenance issues. So it required technicians around all the time. People are going to keep these maintained and up and operating. As we move into the 21st century, we've seen this big boom in telecommunications. And this has led to tons and tons of research on diode lasers and ways of generating light using semiconductors. And so the original early stages, it was lasers at one wavelength. And then communication guys came up with this idea of wavelength division multiplexing. I'll send multiple different wavelengths of light down a fiber. And then we came up with this idea that we can actually make a laser spectrometer where we can actually change which wavelength it lasers at. And there's some things about lasers that are really important to us when we do spectroscopy. They're really bright. They're monochromatic, so I actually don't have that on this slide, but they're a single wavelength. And so that I'll put this someplace else. This whole thing that we do about absorbance spectroscopy, we view it as a linear effect as long as we only have one wavelength going through the sample. So the fact that they're very monochromatic, one wavelength, lets us get good linearity in our absorbance spectrum. The fact we can scan them now, that we can change their wavelength, is really important to us because it means I can go into this spectrum over here and say, well, I'll take that laser and I'll make a measurement here, and then I'll change its wavelength and I'll make a measurement here, and then I'll change its wavelength again and make a measurement here. And I can go through and map out the entire shape of this curve by just changing the laser wavelengths. So having a broadly tuned laser allows us to get the whole shape of that curve at high resolution with a monochromatic light source. The fact it's bright lets us deal better with samples like this. When we have a sample that's dark and dirty, it's got wax in it potentially or clay in it, we have difficulties getting conventional light sources through them. But we've got this intense bright laser now. So this makes it especially suitable for things like crude oils, condensates, things that would normally have too much background. We can start to use the intensity of these lasers to probe and get information in there. The other thing about the particular spectrometer they use is it has a whole bunch of smarts built into it. It has automated wavelength calibrations, automated gain control and how bright the laser is, and that automated wavelength calibration. They do this kind of cool thing with two little Fabry-Perot interferometers, and it gives them a very precise wavelength calibration. And that lets the spectra from one unit be transferred directly to another unit. One of the most impressive things I've seen done with this device is we can put a spectrometer out in the field, build a whole spectral library off that spectrometer, and move it to another spectrometer, and the library transfers over really well. So calibration transfer historically has been a difficult thing for near-infrared spectrometers. And the technology built into this device enables us to be able to do that. So I want to talk a little bit about what we see when we look at spectra in the near-infrared. So this slide's animated. It's going to change on its own. The top spectrum is a natural gas liquid at 420 psi. So it's a mixture of ethanes and propane and butane and things like that. The bottom one was pure propane. The top one just turned to pure N-butane. And you can visibly look at these and say, by naked eye, I could tell the difference between these spectra. For individual components, it's not that difficult. The problem comes in when we have things like a stabilized condensate, where there's a whole bunch of these spectra all sitting on top of each other. That's when the human eye, our ability to recognize the shape of the pattern and say what chemical is there, our ability starts to fall apart when there's a whole bunch of things overlapping. But one of the other technological advances we've seen over the last decades has been both massive improvements in computer speed. Computers are just faster, every year they come out and say, hey, instead of a 2 gigahertz processor, we got a 3 gigahertz processor. We got 8 cores instead of 4. We can crunch more numbers faster. And we've started to use sophisticated algorithms to detect patterns and shapes in all sorts of devices, including even, personal use type devices. Back when I went to university, computer science professors would say that, and artificial intelligence would say, well, we don't really know whether we're ever going to be able to get algorithms that can actually translate human speech because the waveforms are so complex and it's so variable. Well, everybody's phone does it now. Hey, Siri, tell me about that new spectrometer. And it does a Google search for you. And so we have these devices that use this ability to look at waveforms and patterns and turn them into actionable data. That's what we want to do with spectroscopy. We want to take that ability to use pattern analysis to look at those shapes that we see, those waveforms that we see, and say, how do I take that spectroscopic data, run it through a set of algorithms that we refer to as chemometrics, the chemo part basically from chemistry, the metrics part from measurement. How do we take that spectroscopy data and use it to make chemical measurements that we can end up pushing out information? We want actionable data. We want to take that information and use it to figure out things like chemical compositions and physical properties. That's kind of where we're looking to try to get to here. If we're going to use this in an operating gas plant or a crude oil blending skid, we're going to take that spectroscopic data and be able to say, well, I can use that to improve my operations, control my blending, optimize my condensate stabilizer, all of those sorts of things. So we've had this great improvement in the spectrometers. We've had improvements in algorithms, but there's another piece that we need to deal with. And that was the part I kind of touched on early on, is about trying to sample these kinds of fluids. When we look at sort of traditional analyzers, whether it's a chromatograph, whether it's an online vapor pressure analyzer, a lot of these were built around laboratory techniques where we could bring a sample in the lab, we can let it sit there for a day and have the particulate settle out of it. We can centrifuge it, we can do all sorts of things to clean up the sample before we try to take a measurement. But when we go to do that online, if we pull that same sort of technology over there, we end up having these, if you like, sort of more complex sample systems, where we have to do a lot of things like continuous filtering, pressure regulation, flow control, flow regulation. And we also end up having a lot of small tubing runs in there. Both of those work great in the lab, but if I'm dealing with the fluid that comes out of a crude oil well, or the fluid that comes off the bottom of a condensate stabilizer or an inlet separator at a gas plant, those things will have sand, clay, wax, bitumen, asphaltenes, dead mice. I mean, we don't know what's all going to be in there. There's going to be difficult things that make it hard to actually take a sample. And so traditional analyzers in some of these sorts of applications have been problematic, not because of problems with the analyzers, but how do I prepare a sample that's coming from this difficult stream with all sorts of nasty things in it and make it suitable for what the analyzer needs? And so if we want to reduce a lot of those maintenance requirements, what we end up looking at is saying, well, is there a way that I can keep it simple? Can I close couple this solution and improve response speeds and get both faster response times? Because many of these sorts of analyzers, a typical fizz prop analyzer, like an RVP analyzer or a gas chromatograph doing composition, we may see response times on the analyzer in 5 to 10 minutes, and we may have even longer delays than that on the sample system. So a lot of the data that we get can be almost outdated by the time we get it, depending on how fast the process can change. So instead, there's a couple of pieces that have been done to try to take this measurement right to the operating process. And one of the pieces of that is how we actually get the beam of light to go through the sample. So the Virusite flow cell is basically a solid block of stainless steel, 316 stainless steel, which becomes important to us because we concern ourselves with corrosion and NACE. And it has these nice large ports, 1/2 inch NPT, no 1/8 inch tubing. We want nice big ports that things can flow through easily. And so we allow our process fluid to flow through those nice big ports. Big tubing, doesn't plug as easily, can run a lot of flow, helps it be a little bit more self-cleaning. Inside that block, we put a synthetic sapphire core. Looks just like this one. And the beauty of these is they transmit light really well. You can see it's clear as glass, and it transmits light very well in the infrared as well. But the other part of that is it's the second hardest naturally occurring material next to diamond. So it doesn't.
Sorry, really quickly. Sorry. Anybody that was on early enough, you would have heard that I told everybody how you can make that fill bigger on the right-hand side and the presentation smaller. You should be able to pull a little toggle, guys, that's going to come vertical. Just in case you want to see what's in Phil's hand a little closer up, you can do that now. Sorry to interrupt you, Phil. Go for it.
Not a worries, Chelsea. Thanks for reminding them. So the thing with these is that because it's hard, we don't have to worry about it being scratched by sand, clay, bitumen, things like that. And so we can maintain good optical transparency for long periods of time. And in fact, because it's polished so smooth, almost got my smallest soap booth, because it's polished so smooth, the flow going by it, if we run enough flow velocity, it tends to become almost self-cleaning. So we take those two sapphire cores and we put them inside of a block, kind of just like this one. So now we've got these two sapphire cores in there and a nice big flow path for our process fluid to run through. So process fluid is going to be running in. That's where my pen's just about to, there we go. So process fluid just runs in between those two sapphire rods. The black pieces you see on the end here are just fiber optic collimators. So we connect fiber optics and shoot a beam of light through those sapphire rods and through the fluid that's flowing between there. So now we have this process fluid, whether it's crude oil or whatever. We take this beam of light, we shoot it through there, and we bring it back over to the spectrometer. So the advantage we see here is that we have these large flow paths that are going to be resistant to being plugged by things like sand and bitumen. So this lets us kind of change our approach to measurement. Traditionally, we have pulled a sample out of the process, transported it through sample lines over to an analyzer building, and put this analyzer that really needs to be in a well-protected environment inside this analyzer building and tried to condition the sample so it's compatible with the analyzer. Instead, now we move that flow cell out as close to the process as we can. We look for some source of differential pressure. You know, it could be an orifice plate, could be a pump, control valve, could just be some a diameter change or some pipe elbows. We don't need an awful lot of differential pressure because we're really close and because our lines are really short. We typically try to keep these transport lines less than 5 meters. We run nice big lines like 1/2 inch tubing. So we have large diameters, so we don't have much pressure drop. If our direction of flow is going here and we have some kind of a flow restriction, the pressure is higher on this side, so it drives flow out through that flow cell, return back to process. On a condensate stream or an LPG stream, we'll see these running readily with 2 or 3 psi of differential. So we don't need a lot of delta P. We just need something to be able to drive some flow through that flow cell. So we have the process fluid flowing through that flow cell, and then we can mount the analyzer anywhere else. The connection is by fiber optics. We're not bringing process fluid back to the analyzer. So we mount the analyzer someplace like an MCC building, a control room, and we shoot a beam of light.
Sorry, Phil. I'm so sorry to interrupt you. There's a question. Puzic, P-U-Z-I-C.
Yeah.
Did you see that?
Reiko,
okay.
yeah.
Is it?
Hi, Reiko.
You good?
Yeah.
Okay.
Yeah, it was funny. We were just teaching a class this morning and talking about where we put probes and where we take samples from, and how people don't like, it's not a good idea often to go across control valves because the amount of differential pressure changes so much. And so you see people do it a lot still. You go to a lot of existing information and or existing installations, and you'll see people sampling across control valves. But there's certainly issues because the differential pressure changes. And as Bob said, we don't actually need a stinger on the return side. We can return it right back at the pipe wall.
Did you see the second part from Robert?
Yeah. Sourcing from near the centroid of the pipe certainly is where we want to be. So we have that fluid flowing through there, and now we take this beam of light, connect it up over fiber optics, and shoot it through that flow cell, and bring the light back over to the electronics box here. This is where the spectrometer is, and this is really where the brain is. This is where we bring that fiber back, make those measurements of the spectra, and use those sophisticated algorithms that we talked about to take that spectrum that we measured and convert it into actionable data, like C1 through C6 plus composition, C1 through C9 plus, C1 through C30s, vapor pressure, API gravity. There's a number of physical properties that are well related to the infrared spectrum, things like cloud points and pore points. And so we can use this technology to do a lot of the measurements that we traditionally done with conventional physical property type analyzers or conventional chromatography. Because we're close coupled here, mechanically, we get fast response. We have really short sample lines, so we get into that flow cell quite quickly. Similarly, because it's optically based, we can make the measurement quite quickly. So we get a measurement response that updates, typically every 15 to 30 seconds. So having that fast response lets us tighten up control loops. If we're doing things like blending butane into crude, or we're doing things like trying to optimize a deethanizer or a fractionation plant, we can make those measurements quite quickly and provide near real-time control. One of the other advantages is that one of these boxes can handle multiple fibers. So we can do multiple measurement points. JP3 has made this available right now in sort of 3 configurations. A single measurement point, which it seems to be very suitable for things like a small crude oil blending skid, up to 4 measurement points, or up to 8 measurement points. And so depending on how many sample points you have, how many places you want to do the measurement, we can put a different configuration in. And to do a second measurement, it's simply a matter of having a second set of fibers. So I can bring my second measurement out and bring it back. They're completely independent. They use the same spectrometer, but different flow cells and different fibers. So the one over here might be a gas phase measurement at a plant inlet. And we're looking at compositions for allocation strategies. And the one over here could be a condensate stabilizer or a crude oil blending. So unlike a lot of conventional technologies where we'd say, well, if you want to do a different application, you have to put a different type of technology in or a different configuration of the columns and things like that. We can basically use one spectrometer to do multiple different measurements at different places in the plant.
Hi, Phil. There's another question in the chat from Bob.
Yep, from Bob, yep.
Yeah, did you see it?
Yep.
Okay.
So the longest one we've installed up here in Canada, and Dougie, correct me if I'm wrong, it's about 370 meters, 1,000 feet?
Yeah, that sounds about right. Yeah, just shy 935 or something.
Yeah. There's not a limit, or I shouldn't say there's not a limitation, there's always a limitation. The limitation isn't so much any optical parameters of the fiber as much as it's a custom fiber, so there's a cost increase if you go with longer fibers. So there's a point where it gets to being almost, well, maybe I should just put a second analyzer in instead of trying to spread these measurements out too far. So there's a few unique things here now. We've taken measurement right out to the process point, which gives us fast response. We haven't tried to transport this sample, so we don't have to worry about phase changes. We try to move the sample. One of the big problems that happens to us when we're trying to do measurement is we try to move a sample over a long distance through a piece of tubing. We get pressure drops or temperature changes, and phase change happens. We do all of our measurements here at line temperatures, at line pressures. You know, in Canada, we have a CRN thing in Canada. So in Canada, we can go up to 600-pound ANSI class systems, about 1,500 PSI. The flow cell was actually had to be tested to 10 times that to get through the CRN requirements. So it was tested to 15,000 pounds. Sapphire, again, because it's the second hardest material, has great stiffness as well, mechanically strong. So we can run this on high temperature and high pressure processes.
Hey, Phil, there's a question in the chat from Andy. Are multi-point measurements made simultaneously or offset in 15 to 30 second segments, i.e. cycle time?
Good question. I should have mentioned that. Because they're separate flow cells, they're offset. So we measure one, flow cell number one, and let's say we get an update after 15 seconds. We switch the laser to go through flow cell number two, get an update on that one. So if you had 4 measurement points, you may be looking at up to 2-minute cycle time for the 4 measurement points. You can optimize that if you want to. If one of your measurement points is more important than other ones, you can say, well, measure at measurement point 1 3 times, then measure measurement point 2, then go back to measurement point 1, then measure measurement point 3, then go back to measurement point 1. So you can optimize that if you have one measurement point that you really need updated fast and the other ones you're willing to have go slower. Installations then become, because we don't have to put in pressure regulation or a lot of flow control and a lot of these things, installations become relatively simple now. We look for our sample supply point, bring a sample over to the analyzer. We will typically put in a flow switch, temperature transmitter, pressure transmitter. We like to know that we actually have flow to the analyzer. Do we have, what are the temperatures and pressures of our sample? The PSV that's here is just a thermal relief. We don't need a PSV for any kind of pressure protection because of the high pressure ratings of the cell. And realistically, there should have been ball valves or isolation valves shown here and here. And the reason we have that PSV there is if somebody isolates the sample and the liquid heats up, when the liquid expands, we want to let it have a place to release. The IR cell is sitting in the middle, and we bring the fibers in and out and bring them back to some safe place. Often we'll end up just going to an MCC building, a control room, any kind of cabinet where there's a bit of temperature control. The electronics part of this is class 1 div 2, minus 20 degrees C to plus 50. So we do in Canada, certainly we need a temperature controlled environment because minus 20 degrees C is a good day some winters, right? So in the US, a lot of times they'll just put this outside underneath the sunshade. So to give you an idea of how simple an installation can be, this is a crude oil blending skid. So inside here, there's a plant, it was a gas plant nearby that had depropanizer bottoms. So deep prop bottoms are mostly butanes, pentanes, hexanes, and they were getting their deep prop bottoms trucked away. Nobody pays a lot for deep prop bottoms in South Saskatchewan, and trucking costs money. Nearby, there was a crude oil battery, crude oil storage tanks. And they said, well, what if we pipe our deep prop bottoms over? They blend it into the crude oil, make sure they hit the pipeline vapor pressure spec, and we get to sell our deep prop bottoms now as if it's crude oil. So in this skid, this is basically here to blend C4 pluses, butanes, into crude. So the blending is going on inside the building. Sample comes out, goes past my flow switch. My infrared cell is sitting right here. Temperature and pressure is sitting right here. Returns back into the blending skid. No sample recovery tanks, nothing like that. Just take it out over a little orifice plate, a little place where they get some differential pressure. Let's give you a bit of a zoom on kind of what's going on in here. So, we have a little heated cabinet because it's in Canada. So explosion-proof heater sitting down at the bottom, comes in, goes past the flow switch so we know we have flow, goes through the infrared cell, temperature and pressure measurement, return back into the blending skid. Fibers going in and out. Those go to the analyzer that's mounted in where the control room for the blending building is. So, one of the things that we talk about is trying to get reliable measurements. They don't have an instrument mechanic out here. They don't have an instrument guy to maintain this. And so it just sits out there and chugs and runs and runs. We were almost at the point of wondering, well, are they actually using the data? Because we haven't had a maintenance call for this thing for anything. And it's interesting, Doug's on because Doug manages our field service group and he gets a call on a Sunday. We haven't been out there for 9 months, do any maintenance, and the guy phones and says, we lost data communications over a Modbus to the analyzer. We can't blend if it's not running. Can you help us get data comms up? No one had cleaned Windows. No one had done any recalibration. 9 months of continuous operation doing vapor pressure with virtually nobody touching it. Like I said, our flow paths end up being real simple. This is out at a gas plant in Alberta here, taking a sample off of the process line. So the green one is just bringing a sample into the cabinet. The red one comes right back and returns it again. So we mount that cabinet as close as we physically can to where we want to do the measurement. It allows us to get that fast response time, simple flow paths, easy to understand what's going on. Again, the one up here, this is another crude blending application.
Sorry, Phil, there's another question in the chat from Alan.
Oh, thank you.
Is the measurement temperature sensitive? Is the measurement temperature sensitive?
Good question. Yeah. So when we're going to make our models, when we build models around these things. So when we put one of these in, we have to pull samples for the lab and look at the spectra and build the model around that. And so we want to do that over the range of temperatures that you would typically operate at. And so if you see a really big temperature excursion from where you're normally operating, you may have to add additional data into the model. Oftentimes though, if we're going on a processing vessel, if it's something like a condensate stabilizer or a deethanizer bottoms, those are often running around the same temperature most of the time. One of the nice things about liquid is if it's flowing, it's got a lot of heat capacity, so it doesn't change temperature very much as it flows along the tubing, as long as you have enough flow rate. So on some of these, like actually, I think the one up, is this one? Yeah, so on this installation, unfortunately, my pen won't draw. Let me just do this before I zoom that. So on this installation, there's a second tubing run that runs around in parallel to the cell. It's all in 1/2-inch tubing. And what we're trying to do is keep a lot of flow going through those transport lines because it helps them to keep running at the typical operating temperatures of the facility. The more flow we put through there, we have a fixed amount of heat loss to ambient. And so we don't change temperature of the product much from a cold day to a hot day. So there's one flow path that's bypassing and one that's going through the cell. So again, this is a relatively or a simple installation on a crude oil blending skid. We have crude that's being diluted with butane running through a pipe that's sort of off the side of this picture and then returning back. One of those single stream spectrometers sitting right beside the panel. On the panel here, our sample comes in, goes through the flow cell, returns back to process, and we have that little bypass loop. And we're getting a continuous measurement here of, what some people would refer to as RVP. I mean, the spec sort of describes it more as VPCR4 now. So the vapor pressure at a 4-to-1 expansion ratio. And so client specification is got to blend, you can't go more than 95 kPa. The more butane he can push into that crude oil, he buys butane for, $10 a barrel, sells his crude for $50 a barrel or $50 a barrel Canadian, puts that butane in and sells it as if it's crude oil. It's like watering down your whiskey. I mean, it's, you get to sell an inexpensive product as an expensive product. And so you get to increase revenues there, right? Again, this one is sitting on a deethanizer. Deethanizer tower is right over here and the sample panel is sitting right beside it. Closed coupling makes things simple and short line runs make it fast. Simple flow paths, not much for a technician out in the field to try to go, okay, where does it go? It goes into this manifold and then it comes out here and it comes out there. Basically, it's a 1/2-inch tubing run into the analyzer, 1/2-inch tubing run out. Large bore tubing, it doesn't plug. We don't need much for install space. We don't need an analyzer shelter anymore. Process fluid doesn't leave that little cabinet. It's div 1 inside the cabinet. Fiber goes over to the analyzer. Put it in a control room, an MCC building. We don't have to put any kind of special, usually when we put in an analyzer, we say, well, you have a cost for the analyzer, and then we build a life support system around it. I'm going to build a shelter. I'm going to put in gas detection. I'm going to put air conditioning. I'm going to put heating. I got to put a whole bunch of things around this analyzer to try to make it work. Now the analyzer, we're going to say, I just put it in an MCC building. So here's an example of that. Out there in the Canadian snow, we had this cabinet mounted out at the bottom of a condensate stabilizer. It's very similar to the cabinet that you saw on the crude oil blending skid. Flow switch, temperature, pressure transmitters. Mounted out in the middle of the plant. Over here is their MCC building. They put the infrared analyzer up on the wall, dropped power and fiber into it from the top, and it now just sits out in that building. There's no gas coming back there. We don't have to put gas detection in. We don't have to put any special controls around this device now. Really cuts our installation costs. Multi-stream installation that we just did recently for a gas plant up here. 4 streams, condensate stabilizer, fractionation plant, debutanizer, deethanizer bottoms, some C3+ that's going to storage. build all the panels at our shop, drop them there out in the field, mount them on the wall, hook up the analyzer. Again, when we zoom in on these, those are two separate flow paths. Infrared cell, the two white boxes are just protecting the fiber. The yellow part is the flow switch, temperature and pressure right above them. This panel right below it, actually the green, I think, is the temperature transmitter. We use E&H transmitters out there, Doug. Is that the green ones? Yeah. So we've got
Foxborough, actually. These guys, it's an old Foxborough control system type plant.
Right. So we use Foxboroughs for the transmitters.
And
right.
This is an existing GC building. They pulled them out to put this in.
Yeah, right. So they had what happened was the plant had GCs trying to measure the condensate and the debut bottoms. And they said that because of the maintenance costs, between carrier costs, between having to replace injection valves, having to do maintenance on stream switching and all that sort of thing, I think they were saying they were spending $50,000 a year just on maintenance parts, never mind on the labor side of it. And they said, well, if we go in there with no moving parts and put a system in that does these sorts of measurements, gives them the same data, but 10 times faster and with less maintenance, they can see an opportunity to optimize production. So, we have two panels mounted right there next to the analyzer and the other two panels mounted on the wall right nearby it. And so there's 4 streams sitting inside this little building with the infrared spectrometer sitting right there beside it. Fast response, all the data coming in over Modbus allows them to put better control systems in place. I'm running a little bit late here. So a bunch of advantages, we look at advantages and disadvantages of both methods. The big advantages of doing the near infrared methods is that we can measure at process temperature and conditions, as compared to trying to transport a sample and being worried about phase change along the way. We can use large bore tubing for all of our measurements and not put in filters and regulators. It enables us to do those measurements without a bunch of those maintenance parts. We had another client who said that, they on one of their condensate streams on a blending skid, they said they change filters every 2 or 3 days, and just their filter costs start to add up so much. Fast response time, typically better than 1 minute, often 15 to 30 seconds. We can do multiple measurements with one analyzer. So we can do composition and the physical properties all at the same time on the same analyzer. Whereas if I tried to do that on something like using traditional analyzers, I'd have to put in an individual GC to do the composition and then a physical prop analyzer to do cloud point or pore point or vapor pressure. The advantages potentially of a GC are that they do direct measurement. They're measuring an individual peak to get to a component, whereas on the near infrared or any other inferential type analyzer, we have to build models. And the other advantage potentially on a chromatograph is they can do trace components. They'll go down to single-digit ppm measurements in complex mixtures, whereas with the spectroscopy, because most of the spectra overlap, we're primarily looking at bulk constituents, things in that kind of 0.1% to 100% kind of range. Whereas a GC might go down to 1 ppm or less, right? So as we go through, that question from Michael Sprague. Deployments and fuels blending for product certification. Greg or Steve might be better at answering that. We haven't done as much fuels blending up here. We've done butane blending into crude, butane blending into condensate. But if you're looking at it for like blending into gasoline, we haven't done that application up here in Canada. I don't know whether any of the JP3 guys from the US might want to jump in on this one.
Hey, this is Steve. Phil, yes, we have done those applications in the States. Blending into, for gasoline, either blending in or the final control point on the downstream side of the blend.
So if we're doing things like vapor pressure and gasoline or whatever, right?
Yeah, Ron Mon.
Yeah.
Yeah,
Ron Mon as well.
DVPE as well.
Right.
Yeah. So if Michael
sorry,
wants to reach out with any more details, just circle back.
I got a few questions. Paul, how you doing, man? Well, there's one before that. Dealing with water and moisture content impacting the spectrum. All depends on the amount of water and moisture. So typically, if I just quickly go back here for, sorry, just bouncing back to where I can show a spectrum. Typically, we'll see water in the NIR right around here. Actually, that's probably shift a little bit more that way. I think its center is close to 1460 or so. And so if it's not a lot of water, we'll just see it as a background hump that's there. We can still do all of our spectroscopic measurements. If you get huge amounts of water, it can start to overlap some of these. But we had a client who was doing startups on a condensate stabilizer, and Doug and our other service guys would look, we have satellite connect or cellular connection to the analyzer, and they'd look at the analyzer and phone the plant and they say, you know, you guys have water in the bottom of your condensate stabilizer again. You guys got to look at your level control on the inlet separator. So we can deal with some of it in the background, and it does impact the spectrum. We'll sometimes generate alarms saying, we've got an unusual spectrum shape here because there's water there, but we can often get a decent analytical measurement.
And then Paul's question as well. Did you see that?
Yeah, I'm just seeing it now. Hey, Paul, how you doing, man? No, we don't use real-time input of the temperature variations as part of the chemometric models. We try to build our models across a wide enough range of temperature variations that we kind of minimize the sensitivity of that. And the models, as you put in more principal components, basically, or latent variables, you kind of build some of that in as these are the kind of spectral changes we see, but it's not used as a part of the inputs. We don't typically do online validation, so we don't run a validation fluid. What we usually do with customers is say, pull a sample, check. I mean, most custody transfer agreements are based around lab results. And so we tell people, look, pull samples, compare us to what your sample you just pulled at from a qualified lab, and see if we're still in specifications. A lot of the customers that we have that do things like blending will have a local lab, and they'll just say, well, my lab can only get me 4 or 5 samples a day. They get to see how the analyzers comparing to the lab, but they do real-time control with the analyzer.
And then the last one, chemometrics is performed by a commercial. Yeah, okay, got it.
Yeah. I have Eduardo, how you doing, buddy? How's things in Brazil? You have to get me down there again. Yeah, the chemometrics is done basically using a MATLAB-based platform that's running on the analyzer itself. So they don't, or have not traditionally been using second-party chemometric software to do it. With a lot of the installations, especially with launching a technology like this, as a relatively new thing in North America, a lot of it that we've done to date has been using JP3's chemometricians to build the models based on the software that's there. With looking at more international markets, the ability to use other software packages and let people do their own chemometrics is certainly becoming more and more important. And I know, Eduardo, you guys at Petrobras have done a lot of the chemometric stuff down there. I've looked at a lot of the papers that have come out of Petrobras. So I'm going to skip through some slides here. So again, you were sort of saying there's a...
Sorry, Phil. Paul is asking another question. Does the sample cell have a means of easy cleanup for possible fouling?
Yeah, fouling. Yeah,
Fouling?
It's real easy for me because I'm not the guy who has to go out in the field and does it. Doug is, but Doug's done a lot of, they're pretty quick. How long does it take you to do window cleaning, Doug?
It's not very long. You're start to finish 20 minutes easily.
Yeah.
But
Yeah.
if you really want to see, go to YouTube and punch in JP3 and you can see a demo of it. And it's,
Yeah. It's basically 4 bolts on either side of the cell, lets you take it off and get the sapphire rod out. And then it's just cleaning the sapphire rod. And because it's so hard, a lot of times the guys will just use like a rag and brake fluid. Brake fluid's like, it's almost this universal solvent. For some of our systems as well, where they had wax issues, we've, because the analyzer is continuously measuring how much light transmits to the cell, if the optical transmission drops, we have a system in place where we backflush the thing with toluene, and that dissolves any wax that might have built up on the cell windows. So we can automate that cleaning as well. So over the course of the seminar series, we're going to try to touch on most or all of these applications. But where I'm going to kind of focus today is more on this gas plant, condensate sample, stabilization, and NGL fractionation side of things. Oops, well, background just went
A
off.
heads up while you're doing that. There's been a few people that have messaged me asking about the recordings. Yes, everybody, we had some people join us late. The recordings will be available. Thank you.
Awesome. Thanks, Chelsea. So, one of our first applications was really, the first installs in Canada was really interesting for us because we were a relatively new company. We're bringing this technology into Canada, and we get a quote, an RFQ from a big engineering company, and they say, our client wants to measure condensate or butane and natural gas condensate. So, for the US, what you guys refer to as natural gasoline, up here, we were just refer to it as condi, but it's kind of a C5 plus stream. And the engineering company says, we want to measure butane and condi. So we run through the whole job, engineer it, build it, ship it, install it out in the field, and get out there and meet the process guy and the measurement guy. And they go, well, butane's, yeah, it's an important number to us, but really what we'd like is we'd like to know the C1 through C4s in liquid volume percent. Our process guys would like to know C1 through C12 in mole percent. And we'd like if you could give us the vapor pressure too. And we were able to be, we're on site. And again, we're talked back with the chemometrics guys back at JP3 and kind of go, what's involved? And they say, you're going to have to pull a lot more samples. We're going to have to spend more time building models, but we can just model all of that off the one installation. So we ended up being able to tell the client, look, there's no hardware changes. We just have to pull more samples, do more lab analysis, build bigger models. And so what I'm showing here, is a sample from, they had 3 streams of condensate stabilization. And the top numbers are from the lab that the sample was taken to. The bottom numbers are, the Virax numbers are what the JP3 was reading. And so you can see that we have pretty good agreement. There's a little bit of an offset here, 0.3 versus 0.2. Again, a little bit of difference on a couple of these. But in general, we have really good agreement between lab results and our online analyzer. And these are 3 different streams in the plant. So those were the liquid volume percent results. And then down here is the C5 through C12 results. And again, you can see we're typically within 0.1, 0.2, 0.3, maybe as much as 0.5 mole percent, but we're doing a full C1 through C12 analysis and a vapor pressure analysis in under a minute. And they get real-time feedback from this on how to run their condensate stabilizers. And I didn't put the vapor pressure results up there, but the vapor pressure results, again, they're trying to run under 95 kPa, just shy of 14.5 pounds. And oh, thanks, Teresa. Thanks for putting that in the chat. Yeah, if you guys haven't had a chance to register and you want to make sure you get the follow-up stuff like the slides, copy of the slides, and the YouTube, you can just go on the site still and register anyways. So exact same hardware, almost a completely different analysis set, all done and providing them real-time results. We also did a truck offload for this client, and so they were looking at trucks coming in and saying, well, as a truck offloads, this is a C3 plus. What we up here in Canada refer to as C3 plus, the US tends to refer to it as Y grade. But it's a C3 plus hydrocarbon stream. And what they wanted to be able to do was when a truck offloaded is take a data point every minute, look at what flow they're getting off the Coriolis meter every minute, and do a flow weighted average of the composition of the truck. Because this enabled us to do, we gave them basically a full C1 through C9 plus every minute, and they're flow weighted averaging that and saying this is what the value of that truck is. And the reason they want to do it, you can kind of see it at the end of this chart. This particular truck that came off is relatively low in propane and higher in butanes. And the next truck that comes in was higher in propane and much lower in butane. And the butanes and the heavier have a lot more value to them. So they wanted to be able to say, how do I evaluate each of these trucks? The alternative, the way people have traditionally been doing a lot of this, is once a month, they would go and pull one lab sample and say, hey, this is a lab sample from, who am I going to pick on here? This is the sample from Eduardo's plant. And this is what he gave me on this sample. So that's what he's going to give me all month. Well, Eduardo's smart. He knows I'm coming out there on Tuesday. So he makes the best product he can on Tuesday. And then I pay him the most money all month. So instead, they said, I want to be able to look at each truck that comes from every plant in real time. From an installed base perspective, there's over 225 installations of this technology across North America now, over 600 measurement points, pretty much in every active region where there's drilling going on and production going on. There's a good mix of crude, condensate, NGLs, natural gas, NGL refined products. Okay, good question up there from Steve.
Can you read the question maybe just for me, or do you want me to?
No, I get it. I was wondering if Steve, is that Steve Bernardin? Yeah, I'll get to that one right away. Yes. Hey, Steve, how you doing? Yeah, and so we've put a number of applications. We're installing, we just installed one. We got 3 more that we're building in the shop right now up in Canada. So doing the offline modeling. So what we do is when we actually don't do offline modeling. We go out to the installations, pull samples, trigger the device to say we're pulling a sample right now. So the device stores the spectra that it saw during that sample pull. And we send that sample now off to the lab, whether it's a local lab at the plant or a commercial lab like SPL or Maxim. And we get the lab results back. We have a cellular communication to each of the analyzers, so we can pull the spectra that we got, what the lab results, and have the chemometricians back at Austin, Texas, be building the models as needed. So we have done, like the one we just installed where we had those 4 streams out in the field, what we did is we put one of our single stream analyzers out there, let it run, their local lab pulled samples, and we built models around that other analyzer. And then when their 4-stream analyzer showed up, just installed it on site and ported the models over. And if my answer, by the way, isn't complete enough and doesn't satisfy those questions, like just jump in and grill me a bit, it's okay. So on natural gas plants, the things that we look at, is we can do the raw inlet gas. These rich BTU gases are coming from shale wells. We can handle products like the dry sales gas as well, do the C5 plus streams and all the Y-grade NGLs. The benefits, of course, being fast response and minimal maintenance. So now we can start to put in tighter controls on some of these things and allow them to optimize how they're running their condensate stabilizer. Even looking to say, well, based on pricing today, should I run leaner or richer on my deethanizer? Should I go into ethane recovery mode and running in different modes? I use Gregg's figures. We have a completely different issue when it comes to condensate from the US or oil, especially from the US and Canada. US oil tends to be high vapor pressure, got a lot of light ends in it. Canadian oil tends to be low vapor pressure, really heavy. And so in the US, they're often trying to boil off all the light ends and try to get it down to a vapor pressure spec so they can put it into a pipeline. In Canada, we're going, how much inexpensive stuff can we blend into this crude oil before I put it into the pipeline? And so both of them, though, come down to optimizing either a blending facility or a condensate stabilizer. So typically, when we look at something like condensates, or this could be NGL recovery as well, we bring a liquid in at the bottom side. We're taking some of that liquid and changing its temperature, recirculating it back in, using that to boil some vapors off onto the overhead side. So vapors going out over here. And we have product going out on this side. And we want to know, does that product meet specification or not? Generally, the tighter I can run to the specification, the more money I can make. And so, this one uses a little bit more of a Canadian type example, which is in Canada, we're allowed to have about 5% butane in our condensate. So if a guy overstrips it and he's stripping it down to 3% butane, he ends up pushing out less volume. There's an extra 2% production that he just lost by stripping it and pushing it over the vapor side. And so, in simple, we did really small volumes here, but 100 barrels a day, that 2% at $20 a barrel for Condi costs them $2,000. Now, when we talk about Condi running around $50 a barrel now, and when we talk about things like the Encana condensate stabilizers being 4,000 cubic meters a day, 25,000 barrels a day, 1 or 2% increased production is a lot of money. We just did a project for a client who has gone from 400 cubic meters a day to 404, and it prints them about $2,000 a day. So we can increase the volumes by running tighter to the specification. And in this case, we upped it by about 3%, and that allows us basically to increase production yields. We also get better vapor pressure control. So this was a plant that had like a heater treater where they'd overboil for a while, let it cool off, overboil for a while, let it cool off. And instead, when we put the analyzer in, we allowed them to control closer to their set point. They had to stay under 9.5 PSI in the US. ROI comes from all just by not overboiling, you produce more product. So we give a couple of case examples in here, of in this case, it's a pretty big condensate stabilizer, almost 27,000 barrels a day. Manual control, they are running at 7 PSI. When they put the analyzer in control, they ran at 8.5 PSI. The increased yield that occurred because of that in a year generates about $2.9 million. So when we start looking at these processing vessels, what we're looking for is applications where if we can make a tighter measurement, if we can run closer to product specifications, we can increase yield. I kind of joke about it in some ways and tell people the reason we put process analyzers in is so we can make the worst possible product we can that still meets specifications. Because often that means we have less processing and higher yields. And so here, we might have an end user who says, well, I don't really want the light ends. Well, the specification says they can be there. And so now I can increase my product yields. You'll get these slides as well. So there's another use case evaluation here in terms of looking at a gas plant condensates and lease condensates and trying to run at different vapor pressures and showing that if we increase the vapor pressure at different operating points in different operating scenarios based on really just on the volume that's being run through the condensate stabilizer, even the smaller case, which is a 5,000 barrel a day condensate stabilizer, is talking about yields of $600,000 in a year. So we can see ROIs on analyzers that occur in several months. When we look at frac plants, we can go right across the frac train from NGL inlets, deethanizers, deprobes, debutanizers, butane splitters, C5 plus streams. And again, fast response, minimal maintenance. And the important thing is sort of these real-time quality measurements. It allows us to improve our process control. Truck and rail terminals, again, looking at product quality and when it's safe to offload or not offload. Or am I off? We have a client in South Ontario that just says, I want to know when I'm offloading a train car into my butane storage cavern, is it really butane? Am I putting the right product into my caverns? Putting the wrong product in can cost them an awful lot of money. Sorry, I ran through a little bit fast in the end because I realize I'm running overtime here. So what's coming up next? If you have an application, feel free to contact us, whether it's the folks from JP3 and Flowtech or us up here in Canada Insight. We're currently doing a lot of applications anywhere across the hydrocarbon processing industry, from the gas phase side, natural gas liquids, crudes, refined fuels. They're doing a lot of refined fuel works in the US. We are going to do more on this webinar series. So our next one is me coming up in the next 2 or 3 months. We're going to talk a little bit more about the algorithms, how they work, and start looking at some of the applications like we're talking here, crude oil blending, refined fuels, looking at transmix and pipelines is another big one. If we've got a batched pipeline, the infrared spectrometer can tell you when you're on spec for one product, on spec for the other product, and when the stuff in between the two is not on spec for either of those and not a saleable material. So if you want to contact anybody, you can contact Greg out of the US. Gregg Williams is a sales and marketing manager of the US office. He's the guy whose picture just came on. There's Greg. His phone number and email is up there. You can contact me up here in Canada or Scotty or Doug. Be happy to answer any questions you have. That wraps me up. Any other questions you have? Love to talk about them. I'd like to take a moment here to thank Chelsea and her team because they're the ones that kind of make all this stuff happen. They help arrange kind of the marketing emails that go out and the fact that we can get this information out to you, the website work. They help to set up all the audio and visual for this. And as you can see, kind of manage the crowd and just make this easy for me. So I get to do what I like to do is come up and talk about technology well. So Chelsea, Teresa, thanks very much. Take a bow. Yeah, you're welcome. Any questions or other comments or things you'd like to see in upcoming presentations as well? We're still putting together this whole series so we can modify what we're going to talk about based on interest.
We have a question in the chat. Okay, thanks. This is very interesting. Oh, thank you. No, just lovely feedback. That's all.
Oh, okay.
Yeah.
Cool. Well, certainly if anything comes up, feel free to reach out and contact us. We'd be happy to answer or address any other questions that come up.
Phil, before you leave, we do actually have a question here from Ravi.
Yeah.
Do you need to use ATSM methods to help with modeling?
It depends. So we've done some to different GPA methods, ASTM methods, and so it depends a little. One of the neat things, again, about the technology is that you're not necessarily tied to a particular method. So if the person says, I want to do the hydrocarbon composition and I want to compare it to GPA 2103. Well, we can build all our models based on the lab results from GPA 2103 and compare that and build our models to correlate with that. Another guy might come along in the same application and say, well, I want to use GPA 2186. And so we can say, that's fine. We'll build our models around that then. In Canada, we have a specific measurement or method for butane that we call DMC4-. And people say, that's the spec that Pembina is using. So that's the spec I want my measurement to correlate to. So the interesting thing about these inferential methods is that you're not really tied to one particular standard or method that you decide to correlate to.
Thank you. And then Paul has another question. Does JP3 maintain the models, or is that typically done by the end user?
Typically, JP3, so typically the way we've done it is as we get an installation done, up and running, client says, I'm happy with the way the models are running, then we'll say, great. If you want to keep updating them, we'll sell you a kind of a performance guarantee where we'll come out on a periodic basis, take additional samples, add more information on the model. But right now, traditionally, all the modeling has been sort of taken care of and managed by JP3.
Awesome. All right. Does anyone have anything else for Phil? Does anybody have anything else they'd like to say before we wrap this baby up? All right, well, Harris, your turn to take a bow, I think.
Thank you. Thank you. No, thanks everybody for coming. It was great. Thanks for the opportunity to do this. Big again, shout out to JP3 and Flowtech for allowing me the privilege of talking about this technology. I've been pretty excited ever since we got up to Canada, and I've been enjoying getting it implemented out in the field, and they've been great to work with. So thanks everybody for coming.
Thank you so much. Lots and lots of thank yous and great presentations coming privately over me and then also to everybody. So thank you guys so much. Thank you all for being here. Thanks JP3. Thanks Greg. Thanks Jenny. Thanks Floyd. Thanks everybody that's on here. Thanks Phil.
All right. Take care everybody.
Thank you.
Hey, great day everyone.
All right. Bye.
Bye.
Thanks again.
Thank
Thanks
you.
Greg.
Bye-bye.
Bye.
Ciao.